In the last video, we talked about where these equations came from. This is our RC circuit, and we talked about the charging phase as we're charging up that capacitor in the DC circuit. And we talked about where these equations came from. The voltage across the capacitor is going to start at 0, and then very quickly it's going to climb to a maximum value. In this case, that maximum value is going to be E, the voltage source of the circuit. So if we are supplying 10 volts, our capacitor is going to charge to 10 volts. Notice that we see this climb, and we're going to mention all these increments, and that is tau. Okay, so at 1 tau, we're at 63% of that maximum voltage. At 2 tau, we're up to 87%. At 3 tau, 95%, and then after that, the change slows down a good bit. And finally, at 5 times that time constant, or tau, we're going to be at 99%, 99.3% of that maximum value. So let's talk about that time constant. The time constant of the circuit depends upon a couple things. It depends upon the capacitance of that capacitor, how well it's going to store the charge across the plates, and it also depends upon the current through the circuit, which is controlled by the resistor. Because remember, the current is just the flow rate of those electrons. So if we want to charge that capacitor a little bit more slowly, we would want to slow down that current so that the electrons don't get there quite as quickly. So that is why our time constant is dependent upon those two things. So how we would find the time constant of the circuit is we would multiply the resistance, or this is actually the effective resistance of the circuit. In this case, there's only one resistor, so in this case, the effective resistance of the circuit is just R, and we would multiply that by the capacitor value, and that is in seconds. So when we work out a problem in a minute, you'll see where that time constant comes in. So basically, if our time constant is 1 second, then we would see this would occur, this would take 1 second to complete that portion of our charging phase. This would take 2 seconds, and then after 3 seconds, we would be here at 95% of that maximum value, and at 4 seconds, we would be here. And then, of course, at 5 seconds, we are at 99.3% of the final, and we actually assume that we are fully charged or at steady state after 5 time constants, or 5 times tau. Okay, so let's talk about the current as well. So the equation for the current, remember, the current's going to start at a maximum value where we're allowing all the current to flow through the circuit, and then it's going to go to 0 as that capacitor reaches its full charge, and it no longer allows the current to flow through the circuit. So in that same time, if our time constant is 1 second, it's going to take 1 second to get down to about 37% of the initial current through the circuit. And then after a second, we're going to be down to about 13.5%. After 3 seconds, we'll be down to about 5%. At 4 seconds, we're down to about 1.8%. And then after we get to the capacitor fully charged, we're down to about 0.67% of that current. So very, very little current at that point. And the same thing goes along with the resistor voltage as well. We'll be down to very close to 0 volts across there. Because remember, that equation is very similar to the capacitor current equation. All right, so let's apply this to an actual circuit. I've got a practice problem here with 100 volts and 2 resistors in this case. If you want to know what resistance to use, for your effective resistance. It's something called the Thevenin equivalent resistance. You don't really need to worry about what that is. What you want to do is remove the capacitor, just kind of open it up over here, and then short out the source. Okay, and I'm going to redraw it so you see what I mean. We're just going to short out that source, and we're going to leave R1 and R2, so R1, R2, and we remove the cap right here, and then we're going to act like we have an ohm meter, read the resistance between those 2 points. So in this case, that resistor would be reading R1 plus R2, because if the ohm meter is reading from this terminal to this terminal, think of it as a complete circuit where we're seeing R1 and R2 in series, so we would add those. Okay, so that's your effective resistance. So if we're looking for the time constant, tau is equal to R times C, and in this case, R would be 2.2K. Let me get rid of that. 2.2K. Let's try that again. 2.2K plus 3.3K times our 1 microfarad capacitor. So if we do the math there, we get about 5.5 milliseconds. Okay, is that the time it takes to fully charge that capacitor? No. To fully charge the capacitor, that's going to take us 5 times that time constant, or 5 times the 5.5 milliseconds. Okay, so to fully charge this entire process would take 5.5, 27.5 milliseconds. Okay, but this right here is tau. Okay, we really need to know that. And we know that it would take 27.5 milliseconds to fully charge our capacitor. Okay, so find the mathematical expression for the transient behavior, there's a lot of words, of the charging phase of VC, IC, and VR, if the switch is closed at t equals 0 seconds. Okay, so the way I like to approach this is to kind of draw it out. In the previous section, I showed you that in the beginning of the charging phase, our capacitor looked like a short circuit, and at the end of the charging phase, it looked like an open circuit. So let's just redraw the circuit to look like that, and it'll make writing these equations a little bit easier for you. Okay, so I'm going to say at t equals 0 seconds, and then over here I'm going to say at t equals 27.5 milliseconds and beyond. Okay, so at t equals 0 seconds, the switch is closed and our capacitor looks like a short circuit. Okay, so we've got R1, R2, and our 100 volt E here. Didn't leave myself quite enough room to put in those resistor values, but we'll come back and get those. Okay, so, and then once we get to 27.5 milliseconds, at that point, our capacitor looks like an open circuit, right? Where we have V sub C equal to, in this case, that's going to be 100 volts. Again, R1, R2, and our 100 volt source. And then the equations are what happens in between. So I'm going to leave some room in between, and let's discuss what's going on at t equals 0 seconds first. So at t equals 0 seconds, Vc equals 0. It's a short circuit, so the voltage drop across our capacitor is 0. We're starting at 0 volts, and we're going to charge it up to, over here we'll have 100 volts, right? Our current is going to start not at 0. So we have a complete circuit here for t equal 0 seconds. So the current at this point is going to be E over RT for the circuit. And this is just a series circuit with R1 plus RT as our total resistance, 2.2K plus 3.3K. So there we're looking at 18.18 milliamps of current to start with. At 27.5 milliseconds, if we come over here, what would our current be through the capacitor? It's an open circuit, so I would have to be 0. Now let's look at VR1. Here we do have current through R1, so that would just be IC times R1. So that 18.18 milliamps times the 2.2K, which would be about 40 volts. And let's do VR2 while we're here. That would be IC times R2. This is basically just a simple series circuit. We've got the current 18.18 milliamps through two resistors, 2.2K and 3.3K in series. So we'd have about 60 volts there. And when we look at the end, where we've got after 27.5 milliseconds, VR1, it's still going to be IC times R1. It's still Ohm's law. But think IC is actually 0, so the voltage there has to be 0 as well. And for VR2, same thing. IC times R2. This time it's 0 because, of course, IC is 0. Okay, so now it's just a matter of writing in our equations. I'm going to move this over a little bit so that we have a little more room. And you can back up the video if you want to remember where that came from. The charging equations go here. Okay, so for V sub C, we're looking at a value that starts at 0 and goes to a maximum of 100 volts. Remember, that is our 1 minus e to the minus t over tau. And I'm going to replace that with my 5.5 milliseconds. And the maximum voltage goes right here. Okay, so what we're saying is our V sub C starts at 0 and climbs to 100 volts after 5 times 5.5 milliseconds. Our IC is doing the opposite. We're starting at 18.18 milliamps and going to 0. So that shape of that curve looks like e to the minus t over tau. And we're starting at the maximum of 18.18 milliamps. So this equation says we're starting at a maximum and going to 0. What about VR1 and VR2? VR1 is starting at 40 volts and going to 0, so it's going to have exactly the same shape as our current, but this time the maximum value is 40 volts, and VR2 again starting at a maximum of 60 going to 0, e to the minus t over 5.5 milliseconds, but our maximum is 60. And here are the equations. So basically what these are for is to find out the values from t equals 0 to t equals 27.5 milliseconds. Anything after 27.5 milliseconds would be these values. So how would we find, for instance, the voltage at 10 milliseconds? We would just plug the 10 milliseconds into t here. We would just plug that time right into here of our equation, and here, and here, and here. So if you want to practice with that with your calculator, make sure you put this in, make sure you work with this a little bit and see that you can get this correct. But let's just say we want to pick t equals 10 milliseconds. To evaluate v sub c, that would be 100 times 1 minus e to the minus 10 milliseconds over 5.5 milliseconds. Now, since you're dividing milliseconds by milliseconds, you can ignore the milli there because the ratio is still the same. If you were dividing seconds by milliseconds, you really couldn't leave that out, but we can in this case. Let's see, so what would that be? In your calculator, that's 1 minus, and then you do the shift of the natural log function, or ln. You see an ln button, that's what you would use, and make sure you're using the negative sign. And that puts us at 83.77 volts is what we would be down to there. I mean, up to. And then our I sub c, and we'll figure out the VR and the VR1 and VR2 another time maybe. 18.18 milliamps, e to the minus t over tau, so e to the minus 10 milliseconds. Over 5.5 milliseconds. So there we're starting at a maximum and going to 0. And there we're down to a little, just under 3 milliamps at that point. So this is how you would find V sub c, I sub c, or VR1 or VR2 for any time between 0 and 27.5 milliseconds. Okay, let's look at a second problem here. So here we have just one resistor. So if we're looking for the time constant, remember that is R times C, which in this case is the 100 kilo ohm resistor times 5 microfarads. So we're looking at about half a second, or 500 milliseconds. Write the mathematical expressions for V sub c, I sub c, and V sub r. So for this, I'm going to kind of skip doing the drawings again and just say that, remember, our voltage across our capacitor is starting at 0 because it's not charged at the beginning, and it's going to a maximum value. So that shape is 1 minus e to the minus t over tau, which is our 0.5 seconds. And that maximum value we're charging to here is going to be that 20 volts. To write your equation for I sub c, remember, once we close this switch, we're allowing current to flow as we're trying to charge up that capacitor. So we have full current at that point, and the capacitor looks like a short circuit. So and it's going to go to 0 as that capacitor charges. So the shape of that is e to the minus t over 0.5. And IC in this case, if you imagine that this, when this is closed, that our capacitor is a short, then this would just be Ohm's law, E over R. In this case, it would be our 20 volts divided by our 1 to 100 k ohms of resistance, which would be our 200 microamps. And for VR, there's only one resistor. Remember, VR, really, we could just take IC and multiply that by R, and we would get the exact same equation for IC. The other way of looking at it, of course, is that as we increase the voltage across our capacitor, we'll see a decrease of voltage across the resistor to make up for that. But let's do it this way this time, and we'll see that we have 100 k ohms times 200 microamps times e to the minus t over tau, which is the 0.5. So there we see that we're going to start with 20 volts drop across the resistor, and over time we'll go to 0 there. So that's what we've got for our charging equations, or mathematical expressions, if you're asked for that. Mathematical expressions. We would also call those charging equations in this particular case. So how much time should pass before we can assume that the charging phase has passed? Fully charged, if we allow that capacitor to charge up fully, that happens at about 5 times the time constant. So in this case, that's 5 times 0.5, which would be 2.5 seconds. It's happening pretty quickly. Now, let's say we want to figure out what the voltage across the capacitor is, the current through the capacitor, and the voltage drop across the resistor at, I don't know, let's say 1 second. Okay, so at 1 second, that's before we get to that fully charged state. So let's figure out what's going on there. So V sub C, 20 times 1 minus e to the minus 1 over 0.5. If we do the math there, we're at about 17.29 volts at that point. And IC, going to 200 microamps, e to the minus 1 over 0.5. We're down, we've dropped very sharply here to about 27.07 microamps. And for VR, the voltage drop across our resistor, let's see, that's not quite right. Let's see. Right about 2.71 volts there. Okay, I want you to notice something, that if we took our VC plus our VR. That's about 17.29 and 2.71. What would that equal? You guessed it, that's about 20 volts. Okay, remember Kirchhoff's voltage law says that the sum of the voltage rises minus the voltage drops around a closed loop has to equal 0. So if we apply 20 volts and we have 2.71 volts dropped across R and we have 17.29 volts dropped across the capacitor, that actually equals up. As we go over time, this voltage across the resistor continues to drop while this voltage across the capacitor continues to go up. So we're going to see that the sum is still going to go to 20 volts. Okay, one mention about our steady state conditions. When the circuit above has passed approximately 5 time constants, we expect the circuit to be at what we call steady state. In steady state, the capacitor behaves as an open circuit in a DC circuit. What that means is our current is equal to 0, the voltage dropped across the capacitor is at a maximum level. And it should theoretically stay there the entire time, okay? Until something else happens to either discharge the capacitor or to charge it fully if we didn't allow it to charge in the first place. We will work more on the steady state at another time, and the discharging phase is yet to come as well. And that's all.